anyway, back to the lecture. So picking up where we left off, this is now a week ago, we were talking about this idea of shear flow for beams that are, thin-walled beams. And we started with this example. I'll go ahead and open this image for you. This was a hat section. So this is the cross section, and it goes off into the depth of the plane here. It is still a beam. It is still much longer in one direction than it is in any direction within the cross section. But in this case, it has this predominant feature, that is that it has a thin wall. Now, when we have a thin wall, of course, we define that idea of shear flow, which was shear stress times thickness. And then we started to develop equations for how shear flow evolved. And I'm going to go back to one of the equations just so that you guys have it fresh in your mind. This was the equation that we developed. Obviously, it's a rather lengthy equation, but it's not terribly difficult when you study the individual components of it. There's some geometric components, the I values. So this is the area moment of inertia and area product of inertia. Of course, you guys know there are three of them. So IXY, IYY, and IXX. Those show up sort of repetitively here. And then we have geometric terms associated with where we are in the cross section, that is either X or Y measured relative to the centroid. And that shows up in two places, just multiplying different terms. And then last but not least, of course, there's the resultant shear on the whole cross section. That's shown up here, SY and SX. For this cross section that we're examining now, we see that it is symmetric about the x-axis, so that means IXY goes to 0. So that set of terms goes away. And as you may recall from last time, I said that we're going to assume for our current calculation that we had a y component of resultant shear. So SY is non-zero. We were going to assume that SX was 0 for our calculation. So basically everything down here went away. And so when IXY goes away, we can then cancel the IYY terms that remain here, and lo and behold, this all simplifies to be this equation. So the shear flow is equal to some constant. This is a boundary condition, really is what it is. Shear flow at some edge, at some position defined by S equals 0. That came out of an integration that we did. So it's just an integration constant now that now acts as a boundary condition, minus the integral of the thickness, which could theoretically be a function of position, times y within the cross-section, the y position within the cross-section, integrated over the arc length of our structure, times the resultant force over IXX. And then we began to do this problem. Again, a simple problem. This cross-section, this load, what we found, one of the things we found was at the boundary where S equals 0, the shear flow was 0 because there's 0 shear stress at that point. And so in this particular example, at one edge, we could say that Q0 was 0. We also broke up this integral such that it had several different S's. We defined local coordinate frames, one starting here and going this way, the next one starting here and going this way, the next one starting here and going this way, and so on down the line. So we actually had 1, 2, 3, 4, 5 coordinate systems, S1, S2, S3, S4, S5. We had 5 constants of integration. One of them is going to be 0. The others are going to be the value of the integral as you go from one side to the other. This is all just review, so I'm going through it fairly quickly. And the other thing we could identify in this image is that for various segments, i.e. within each of the S sections, the thickness was constant within the section. And because the thickness was constant within the section, for the purposes of the integral of that section, we could pull it outside the integral. And now it just becomes a matter of, can we integrate this y as a function of s over this distance ds and then multiply it. So of these terms, within any given section, obviously the overall resultant on the cross section will be constant, The area moment of inertia will be constant. We said t was constant within any given section. And so really now we have just, all we really need to figure out is the integral of y of s ds for this problem. Okay, and then the next thing we did is we just identified what y was. Y being the only non-constant term. So in subsection 1, that was from here to here. The thickness was constant at TA, the boundary condition was 0, traction free along the left edge, and y was actually constant with respect to the centroid, so the distance from there downward was always constant. Okay, it's worth noting that, and I want to make sure this is clear, because I'm not sure this came out terribly clear last time. So we said that the centroid, by sort of visual feel, we know it's basically it's the average of the material, average location of the material, so it's going to be in the center. And what we actually are doing here is we're defining, we need to measure y from the centroid. And so what I defined actually is a local coordinate system. So, we'll call it x1, y1, which is different from xy. And then, of course, in this coordinate system, y1 is equal to 0 along this edge. And then going between the two coordinate systems, of course, the distance from y1 to the centroid, we're going to call this distance yc. Okay, so that's where the yc came from, the centroidal height from the centroid down to the midline of this segment. And the reason it's negative in our equation is because it is obviously downward relative to the parent coordinate system. Okay, so that's where the yc came from. This one, we were running out of time. I didn't necessarily make that super clear, I don't think, last time, so I'm going to clarify it again. Here we're defining our new coordinate system, S2. So S2 starts at this location here. It lives in each of these two coordinate systems, and relative to the centroidal location, we're down minus yc, and then we add to it any distance S2. So if we look at this equation, down minus yc plus any positive S2 gives us y. This is measured relative to the centroidal location. So y is a function of S2 minus yc plus S2. Similar arguments are made for the remaining sections, and I know we got through all of this. So what is this one here? Again, y, just going back to our blackboard. So we're really talking about this height. We need to know its relative location to here. So we say relative to this coordinate system, we went down yc, and then we went up the length of this beam, which we called L. So this total was L. So minus yc plus L is what this segment is. And then the next segment is that height, but now we're starting a positive S4 direction measured down that way. So now we subtract S4. And then the last one, of course, is being symmetric with the previous one. We already knew what the y value was. So again, it's minus yc down to here. So those, we need to be very careful with these geometric descriptions of the positions within the cross section. They're not always going to be this easy. In some of the homework, they'll be a little bit more complex, but always come up with a way of defining where your centroid is. You can then define any number of other coordinate systems you like in order to find a convenient way to write your distance, x or y position relative to that coordinate system. And I hope now this is clear. Last but not least, of course, these Q values, these integration constants, since they need to be renewed for each integral. We had one from here to here. We have one here that applies, it's an integration constant, essentially setting the value of Q at this edge. And then going upwards, and then we had one here and going this way, and we had one here and going that way, and so on. So all of these Q values are now relative to the prior integration. We're starting at the left edge, we're working our way around. Okay, Nicole asked a question in the chat window. She says, why is Y of S3 not plus YC? Okay, so that's a good question, Nicole. Let me go back to this. Oh, which page was my Blackboard? Gotta find my, there it is. Okay, so the distance from here down to the bottom flange is YC, because we're defining our one, a coordinate system of convenience here at the bottom, and we know from the bottom we go up to YC. But the thing is we don't know where YC actually is. Okay, this is a distance. We know it's a distance. I drew it where it was because I know it's generally in that area. However, I could easily have done this. Okay, here's my hat section again. Okay, pretend it's symmetric. I don't know where YC is. Why not call it here? I actually have to do the calculation to determine where it is. So now this distance here, obviously the length from here to here is not the same as the length from here to here. Two very different lengths. So we don't know where YC, we don't know where the centroid is, so we're measuring it relative to a coordinate system. So I'm measuring it relative to this one. So it's positive YC to go from our current coordinate system up to the centroidal location. And then the position of this relative to the centroid then comes back minus YC. The distance from here upwards is a different length. Okay, so I've now kind of picking up the remainder of this calculation now. I think I ended with this slide previously. Note that the above equations each use a local S value, so S1, S2, S3, S4, S5, and have an appropriate boundary condition. The global and local S coordinates are shifted by the position along the beam. Okay, so I think that's fairly clear at this point. All right, so what we need to do is we actually need to calculate what Q is. And remember, it's an integral. Okay, since Q is an integral, we have to integrate. And, let me go back just to the slides. Here's the integral we're doing. It's really Q0 minus, now in this case, T has come outside because it's constant. Sy was constant over Ixx. What remains inside, this is T of S, by the way, but it is a constant for each segment. So this is now Y of S ds. So this is the integral we're doing. Essentially, Y of S ds times a constant. And so if we integrate Y of S for each subsegment, here Y was a constant, here Y was linear with S, here Y was a constant, here Y is linear with S, and here Y is a constant again. So if we do these integrals, the first one was a constant. So what we're really integrating is we're pulling, since the integral of Y of S, where Y is a constant ds, since this Y of S is a constant, it can just pull out. And then we're just integrating ds from 0 to L. Okay, or really from 0 to S1. So if we're making this a function Q, this is the shear flow as a function of S1. So the integral of ds1 is simply equal to S1. Okay, and when we evaluate the magnitude of the shear flow all the way at this corner here, which is a distance L, so that magnitude will just be S1 equals L. So it's L times TA times SYYC over IXX. So that became a really simple integral, no problems whatsoever. High school kids can do it. Probably one of my neighbor friends, his son is in junior high and already doing calculus, believe it or not, and would have no problem with that. Any of these integrals that we're doing, actually. The beauty of this technique is this becomes very comparatively easy to actually implement. Okay, so what we have solved is the Q value within one segment, one arm of this section, cross section. We can conduct the next integral. Of course, from here to here, we saw the value of y was now a function of s, and it was a linear function. So what ends up happening is we get a linear term and a quadratic term that falls out of it. And then the other thing that we need to recognize is that the magnitude in this section 2, the initial value of the constant Q0 for this segment is the value of the function Q1 of S1 at the position S equals L. So as we go back down here, we plug in Q1 of S1. S1 equals L. So we plug in the L there, and then this kind of comes down right here. Okay, so again, what have we done? We integrated once with respect to S2. It was a linear function of S2, so now we get a quadratic result, and this is the outcome. We integrate the next segment. Okay, note we're going to do the same thing. We're going to evaluate Q2 at S2 equals L to get the boundary condition. So just in your mind, do that right now. So Q2 at L, you'll put in L here and L squared over 2. And then this term, of course, continues forward. And so when we integrate the next one, we end up with, because we're now integrating this segment right here, the value of y is a constant, so it becomes, when integrated, becomes linear. So we're now linear in S3. And of course, the boundary condition was applied, and that was brought down and now kind of lives out here. So rinse and repeat, do it one more time. Now we're doing this section. Again, we're applying Q3 at S equals L to be the boundary condition right there. So if we plug in S3 equals L, this wraps around and comes into here. From here to here, y is a function of S. It's a linear function of S. So we're going to get a quadratic equation again in S4, and you check it. Here it is. So we have a linear term, and we have a squared term. It's getting a little bit more complicated because y itself was a little bit more complicated, but it's still integrating a linear function, and you guys could do it in your sleep. So there's Q4 as a function of S4. And last but not least, of course, we're going to have to integrate Q5. That's going to require us to say, okay, we need the boundary condition, which is Q4 at L. So we plug in L into this equation. We bring that forward. That lives right there. For this segment, y is a constant. It's not a function of S. So when we integrate with respect to S, we're going to get a linear term. That's right here. And there we have Q5 of S5. All right, I'm going to pause there. I know I've been jumping back and forth between slides. I know that that can be hard for you guys who are trying to write these equations down to keep up. So I will pause. If anybody needs me to go back a slide or two, I'm happy to go back a slide or two so you can capture that. And while we're waiting for people to finish writing down anything they need to write down, I'll take questions that you may have on this aspect of what we've done. All right, no questions so far. All right, can I move forward? In fact, let me ask it this way. Oh, so Dylan wants to see Q4 again. There's Q4. Let me go ahead and remove my marks so that it's easy to see. All right, so before we move on to the next thing, let me summarize what we have so far. We have calculated shear flow in this cross section. We have a resultant load. That's the total load on the cross section. And from the total load, we've calculated the shear flows. And got to keep in mind, what is shear flow? Shear flow is shear stress times thickness. Okay, so the shear resultant, the total shear load, is the integral of all the shear stress over the cross section. The shear flow makes that a little bit easier because we know that the shear stress is constant over the thickness. So we define shear flow to be equal to the shear stress times thickness. And the result ends up being a force per unit length quantity. And so what we now know is at every point within this cross section, we know how much force per unit length occurs. It's also notable that the direction of the shear stress, it's aligned with the direction of S. Of course, there's the plus or minus sign to indicate direction relative to S. Could be to the right, could be to the left. To the right would be positive, to the left would be negative. But it is a force per unit length along this section in the direction of S, and we've calculated its magnitude. Okay, so then the question becomes, what next? Great, we have shear flow. It's not necessarily meaningful to us yet. How do we use it? Well, let me remind you of a couple of things. First of all, shear flows themselves aren't terribly useful if that's all we think about them. If we stop there, we'd still be a little bit confused because shear flow is not shear stress, differs by thickness, so it's not something that we can use to evaluate failure. But what we can do with it is instead evaluate force. It is a force per unit length. And then what we can do is we can try and figure out what the resultant force is. Let me go back. Let me create a blackboard here. I'm going to draw this one more time. Okay, so from here to here, we have a shear flow, which we know, which, oh, by the way, we could replace with a force, a statically equivalent force. We can also replace this one with a statically equivalent force. We can do the same here, we can do the same here, and we can do the same here. So I'm going to say that we're going to call this one F1, that's force in segment 1, F2, force in segment 2, F3, force in segment 3, F4 is force in segment 4, and F5 is force in segment 5. And we can now calculate what the magnitudes of those forces are, because what we know is the force per unit length, and now we can integrate along the length. One other thing that we recognize, the original force, which was Sy down here, has to be equal to the sum of all of these other forces. This Sy is the static equivalent of the sum of all these forces I've drawn. So bottom line, what we're going to do is we're going to go through and calculate 5 forces. Note in this image that I have the direction that I've drawn these forces. Okay, they are in the direction of the positive S direction. It's good. It's a very good idea when you start these problems, if you're going to define multiple coordinate systems, define Q. So here's S1. In fact, let me make this bigger. This is just one segment. Okay, that goes up there further. In one segment, I'm going to say, okay, here's my S1 direction, here's my Q, and here's my resultant. So this is Q of S and F1. Note, I drew them all at exactly the same time so that I never had any confusion about which direction they were, because we don't want sign ambiguity. The forces are always defined with respect to the relative coordinate system with the equation we're doing, and then we let the force balance keep track of the sign for us. Okay, so anyway, now we are going to do it. Before we do that, before we calculate those resultant forces, note we can also calculate the moment of inertia. In order to be able to calculate the moment of inertia, we actually have to locate the centroid. So those two calculations, I'm going to go ahead and do them now, just for sort of completeness. It's also worth noting that because this thing that I've drawn 10 times now, it's symmetric with respect to the x-axis. We know that the centroidal location of x is on that line of symmetry, which was very poorly drawn. Okay, so x is going to be somewhere along this line, and so we're really only calculating the y value of the centroid. So in order to do that, remember, by definition, y of the centroid is the integral of y dA over the integral of dA, which can simplify. You can do this as discrete sums rather than integrals. Sums are sums, integrals are sums. And so I'm going to calculate the total area of the cross section. That's pretty straightforward. If I look at the image, the total area is, so we have 1, 2, 3 sections that are of thickness TA, and they're all of length L, so 3 LTA. We have 2 sections that are of thickness TB and of length L, so plus 2 TB. So the total area is 2 TB times L plus 3 TA times L. It's very simple. And now the integral of y dA can also be expressed as the sum of the sort of local centroids of the various segments I. So I have 5 segments, so we're going to sum from 1 to 5, so I equals 1 to n, of the local centroid times the local area, and that ends up being equal to 2 times TBL, L over 2, plus TA times L. So those are L squareds. I just left them as they were. And then last but not least, we can calculate the y centroid. So this is just, really simple stuff. You guys could do that as freshmen or sophomores. No problem whatsoever. David asks a question. Do we care about the areas of the corners? Oh, you're jumping ahead, David. What a great question. The answer is sort of plain and simple, the answer is no, we don't. But we have to be able to justify that, right? We can't just say, oh, forget it, I don't need to know it. We actually need to figure out why we don't need to know it. And so the answer to your question really, David, is as follows. If we look at this cross-section, in the limit of these segments being thin, then the impact of those corners becomes negligible. So the thinner these segments are, the less we care. And in the calculation I've done on the prior slide, I'm assuming that the ratio, which is functionally now TA over, I guess you could say 3L, or you could, 3L is a reasonable representation of a length scale within the cross section. So TA over 3L is small. So if TA over 3L is small, then the area of the corners is negligible. All right. Now, so since we've talked about that, I want to then recognize that you can still use this theory even if TA over 3L is not really small. If it was 10%, is that small enough? Well, so you can do the calculation just like I've done it. If it was 10%, you'd get an answer. The thicker it becomes, the more error creeps in. So if it's very thin, the error is trivially small. If it gets to be 10% or 15% maybe, then you might have 10 or 20% error in the calculation. But if you're just trying to do this sort of as an order of magnitude estimate of what the overall stresses are, if you don't need to be accurate to more than 10 or 20%, then you can get away with doing these calculations even if that thickness ratio isn't really small. You just have to be cognizant of the fact that the error builds the thicker it gets. Okay, the other thing, so now we've calculated the centroid, which, by the way, if you look at what the centroid is, it ends up being L times some ratio of the thicknesses. And it's measured, of course, from the bottom. It's measured from down here. So it's some fraction of L, and lo and behold, it ends up being in here somewhere, just like I had placed it previously. Obviously, it depends on how long this is. It depends on how long this is, and it depends on the relative thicknesses of each. For any reasonable combinations of TA and TB, it's going to be in the middle here somewhere. Okay, then of course we can calculate the moment of inertia relative to that centroidal location. And this calculation is fairly straightforward. You guys have done these in past courses, so I won't go into much detail other than to say that for a cross section that has this geometry, where we have sort of rectangular segments of the geometry, it becomes most convenient to use parallel axis theorem. And so the solution that I've presented here is a parallel axis theorem calculation of it. So these here, parallel axis theorem of this one, so this is one segment relative to YC, gives us this. So what does parallel axis theorem say? Well, it's the local IXX value plus the area times the distance squared. So locally TA cubed over, so it's a rectangular section. Of course, we remember the I value for a rectangular section is BH cubed over 12. In this case, H is the thickness, B is the length, so BH cubed over 12. So this portion is the local plus the area, which is the thickness times the length, so TA times L times the distance from the reference point squared, so that's YC squared. So this, as I have indicated, is for one segment. Of course, there is another one here, so we multiply by 2 to get both of them. We can do the same type of argument for now our vertical sections. So locally, it's base times height cubed over 12. In this case, the height is the length, so TB times L cubed over 12, plus now the area times the distance from the neutral axis. So the distance in this case is the midpoint minus whatever the YC value was. So that distance squared. And then, of course, there are two of them, one here, so we get a 2. And then the last one's the same arguments. That's the top flange up here. And we get LTA cubed over 12 plus the area times the distance from the neutral axis squared. So that's IXX. Pretty straightforward. Okay. The last thing to pay attention to here is that we need to calculate the shear stress. And the shear stress, by definition, you recall we defined Q as being equal to the thickness times the shear stress. If we solve for shear stress, it becomes Q over T. That applies for each individual segment. Since we know what Q is and we know what T is, we can go ahead and say that we know what shear stress is. We can plot shear flow and shear stress, which I've done. Now I want to spend a little bit of time staring at these. First, let's look at the shear flow calculation. This plot is a plot of shear flow for each segment. Now note it's in the global S-coordinate system. The global S-coordinate system we defined. We had local S1, 2, 3, 4, and 5. The global will start here and will just increase as we go around. So the global is essentially 5 lengths now. By the way, I plugged in some values. This used to be a homework problem, which I've converted into a lecture problem instead. So I had given lengths, and I had given loads, and values of S and values of L and values of T, and we can calculate shear flows. So importantly, in that first segment, we said Q was linear, and so it shows up as being linear. In the second segment, QS2 was quadratic. You can see it shows up as being a quadratic equation. S3 was again linear, and you can see in the plot that is now linear. Q4 was quadratic. Again, it shows up as quadratic. And then S5 was again linear. It's worth noting that this is a flow, and in some ways it's describable just like a fluid flow or a current flow of some other form. That means that there has to be a degree of continuity to it as you go around corners and so forth. So you can see as we go from Q1 to Q2 to Q3 to Q4 to Q5 that the value of the boundary condition is consistent with what we described previously. So here at this interface between Q1 and Q2, the initial value of Q2 is equal to the value of Q1 evaluated at S1 equals L. So it's this continuity argument for shear flow. Some other things that are worth paying attention to in this plot. Of course, we go back, and if we looked at the original problem, we knew that at this left edge, this was a traction-free surface, right? This goes off into the distance. The beam was not loaded exteriorly on the edge. It was traction-free, so the shear stress at this point has to be equal to 0. Consequently, of course, shear flow, which is shear stress times thickness, also has to be equal to 0, so we need it to be 0 at the left edge. We need it to be 0 at the right edge. And as we look at these plots, what do we see? Well, we see it 0 at the left edge. We see it 0 at the right edge. Not quite as obvious, but something that comes with experience is that with a cross-section that is symmetric, loaded symmetrically as we had here in this problem, we need there to be some symmetry about the symmetry plane. In this case, that symmetry is actually anti-symmetry, so it's going to be anti-symmetric relative to that symmetry plane. So you can see it's positive shear flow on the left side, goes back through zero at the midpoint, because in order to be anti-symmetric, it has to cross zero at that symmetric plane, becomes negative as we go further down, and then eventually comes back to be zero. Are there any questions about this shear flow plot? I hope it makes sense.
Will the zero and the middle always intersect exactly at the midpoint of the hat beam?
So the answer is no, not as a general statement. So when will it not? It won't if the thing's not symmetric to begin with, and there are many structures that don't have symmetry. You know, the symmetry has to be both in sort of geometric position, but also in thickness. And lastly, it also has to be symmetric in load. So, you know, by contrast, let me go back here. Here's my blackboard. I'm going to delete it for a second. Okay, if I had drawn a symmetric section, but let's say that the resultant moment was, or the resultant stress was actually out here instead of on the midline. Well, this presents a little bit more of a challenge, and we're not there yet. We have not done torsion of these thin-walled segments. But what I'll tell you is that what you're going to do with a problem like this is you're actually going to move it to the symmetry line and then add to it a corresponding moment. So if this was the actual SY, we'll call this SY prime plus MZ. So SY prime plus MZ has to be the static equivalent of what SY was. Okay, we'll get to that later in the semester, but it's more complicated than I wanted to give in this introductory example. But that's the direction that you end up having to go. So you're gonna get symmetry in one portion of the, you're gonna get anti-symmetry in one portion of the calculation, but then you're gonna also have to add to it the shear flows from the torsion, and the shear flows from the torsion would then break the anti-symmetry. Amir asks a question. For beams with T or I sections, what the global S would look like. So that's a great question. You're going to get homework to address this problem, or this question, really. So what Amir's asking is something like this. So if I had, as an example, an I-beam, okay, and by the way, there's no reason for this to be symmetric. It could be something like this. And you could define unique S-coordinate systems at each segment. So I could define one here, I could define one here, I could define one here, I could go here, I could go here. Note that what I've done, it starts to get a little bit confusing because now you have two converging S's. So it's positive this way, positive that way. You might instead say, okay, I don't want that one to be that way, I want it to be this way. Okay, that makes sense at some level. But the problem is where you have these intersections, it's not obvious. Like, so now this one, in order to maintain its positive nature as I defined it at the bottom, it's going inwards here. So this is in, and out. It gets a little confusing when you do this. And if you track the math correctly, if you track your signs correctly, you will get it right, but you have to be careful about that. And to get back to the question as asked, for this, there is no convenient global S value that would be functionally equivalent to what I did to get this this plot. So if you wanted to, if you had a problem that was like this, let me redraw just portions of it here. So if you had this problem, you'd have to instead come up with a way of plotting, okay, here's my shear stress here, here's my shear stress or shear flow here, here's a shear stress here, Here's one, and then here's one. You know, some way of representing those differently than the way I did it in the example problem. Okay, so that was shear flow. Unless there's any other questions about shear flow specifically, I'm going to highlight then the next figure. That's the one to the right. And what do we recognize? So instead of plotting shear flow, I'm plotting shear stress. And of course, as we examine the shear stress equation, we see it's the shear flow divided by the thickness. And as we go back and look at the beam, that's this beam here, of course, we see that there is a discontinuity in thickness. It's one thickness here and then a step change in thickness there. So because of that, we would anticipate a step change in shear stress. So if we look at this image, this plot, we see that as we go around that corner, we actually get a step change in the calculated shear stress. So from here to here, then it got thicker, so the stress goes down. Then it got thinner, so the stress goes up. Then it got thicker, so the stress goes down. Then it got thinner, so the stress goes up. Still zero at the edges. It's still traction free at the edges. It's still anti-symmetric, so it's still zero in the middle. But you get these discrete jumps in theory predicted shear stress at those corner locations. Now, that presents an interesting thought process, right? Is that physically real? Somebody take a shot at answering my question, please.
I don't think it's possible.
Who was that, David?
Yeah.
Yeah, so thanks for sticking your neck on the line. David, you're right. It's not really possible. This is not what happens. This is what theory, at least this is shear flow theory for thin-walled bending. That's what our theory predicts. Let me get my chalkboard back out. Okay, so I'm going to draw. We started up, and then we have this jump, and then we have this jump. Okay? Now, that is what theory predicts. In reality, if you plotted stress, once you get to this corner, and I'll draw the corner, as you're flowing around this corner with shear stress, it turns out that this corner does not idealize. In the corner, we get something that's akin to a stress concentration in some sense, but it's a change in shear flow, how it's carried. Okay, and so what we're doing is we kind of actually round down a portion of it and round up a portion of it, and it ends up being something more like this. Except potentially in the exact corners, and then you to actually calculate what the shear stress is at that location. If you wanted it precisely, because it's a stress concentration, you would have to do a finite element model or something else that would be similar. Now, that gets us to some practicalities, right? So if this were an ideal corner, and this were an elastic material, you'd get what amounts to an infinite stress concentration would exist there. But then I would go back and argue, well, David or whoever made the claim, yeah, it's infinite. Well, keep in mind that these structures don't come out of nowhere. They come out of real manufacturing facilities where in order to get this hat segment, they probably bent a hat segment out of flat sheet metal to begin with. So this is probably more realistically a rounded corner, something like that. This is more physically reasonable. And the more rounded that corner, the less stress concentration, the more it actually begins to look like what I've drawn here. So this scenario where the drop kind of gets mitigated a little bit is actually really quite accurate for real world geometries. What does that mean? That means that we can live with this theory and do quite well. Does that make sense to everybody? Excuse me. I'm not really seeing faces at the moment, so can give me in the chat window or something so that I can know that you guys hear and understood. I don't want to move on until I'm fairly confident you get it. I've gotten one response. Thanks, Gavin. Are the rest of you with us today? All right. Thank you, Nicole. Thank you, Ethan. Okay, it sounds like you guys are getting it. All right. So, you know, and the next couple of slides are just me now typing out and, you know, having it ready. I've already described all these things. So we're checking if this is reasonable. We check the shear flow at one edge. We check the shear flow at the other edge. In both cases, we know that the shear stress is zero. It's traction free, so the shear flow is zero. That showed up to be correct. We checked the beam symmetry, and actually that was anti-symmetric in shear flow. So we checked Q3 at L/2. That's the position, and that showed up as zero. So that was good. All that stuff is as we described. I'll leave this slide on the screen. So if anybody wants to copy, if they hadn't written something to that effect already and wants to copy this, they can. Outside of that, the next topic will be a really cool one, something that I think to this day, it's still one of the coolest things that we can demonstrate in person in lecture, which of course we can't do in person in lecture here this season, but or this semester, I guess. But it'll be a neat little topic going forward. All right, I can tell by looking at your faces, the faces I can see that there are still some writing, so I'm going to go ahead and give you the time to complete that. Okay, I think by your faces, it appears that most of you are finishing up or finished. So the next topic is really an interesting one. It's conceptually something called the shear center. Now, what we did, this calculation that we just did, of course, it can be done for any thin-walled cross-section in bending. But what we need to recognize is that this calculation we did here the way I drew this up, I described there being a shear resultant, and I said it was through the line of symmetry here. What I didn't tell you at the time, which now you need to recognize, is I drew this through something called the shear center. So it is effectively, the resultant has no twisting moment. This shear stress that I drew, shear resultant force actually, caused this cross-section to bend, or this beam to bend, without twisting. And then, of course, David asked the question to get a little bit ahead. You know, he said, well, what happens if it's not through the center? What if it's out here? And I said, well, you know, that's a great question. What we're going to do is we're going to move it back and then add a moment, right? So that's what I said. I moved it back so that the resultant was through something called the shear center. And what I really mean is the following. I'm going to skip ahead in the calculation to the definition of the shear center. The shear center of a cross-section is the point in the cross-section at which the resultant shear load must be applied in order for there to be no twisting in the beam while it bends. Let me say that one more time. The shear center is the point and this is relative to the cross section. So there is a point somewhere in the plane of that cross section that if the shear load resultant passes through that point, then there will be no twisting of the beam, it'll just bend. Now, by contrast, and this is this is something that's so much less valuable, sort of the physical intuition that goes along with this, much less useful in the online lecture setting relative to me bringing my props to class and having you play around with the props physically in class. Okay, this is our beam, right? So simplify it into a 2D cross section, looked like this. Now, if I applied it here, you might say intuitively that that thing is not going to twist. And what I mean by twist is it's not going to end up looking like this, right? It's going to bend. I misplaced my phone here for a minute. I love children's toys. These are musical, thin-walled cross sections. Okay, there's a whole octave of these. My son, who happens to be in second grade, their music teacher, the kids bang on these and make music on the gym floor. It's kind of cool. Anyway, so there is a point where the shear resultant will cause this thing to bend, but it will not twist. Okay, and I do. Oh, no, you were close. Yeah. Oh, you saw it, right? All right, you're cheat. Did you cheat? Here it is, D. You cheated. You just saw it on the screen. Nice, nice, Ethan. If you have perfect pitch, that's just such a blessing. I wish I had it. Anyway, well, so that's tangential, but I'm pleased to know that if you have perfect pitch and you were able to discern that I got that, then I'm very pleased that these are actually on pitch. But I still think you might be pulling my leg. Anyway, so here we go. So if you guys can say it makes sense if I load through this symmetric section that it's going to bend but not twist. And probably if instead I had drawn an arrow out here, you would have said, well, or I'll draw it the other way. If I had drawn one like this, you might have said, well, yeah, it's going to both bend and twist. And so it's actually there's going to be this angular change here, some alpha that it's going to twist in addition to any bending that might be present. Okay, so the intuitive description of this is for any section, and it doesn't really matter what the section looks like, there is a point somewhere in this plane where if I load through the point or not through the point, so I'm going to draw it, let's say it were here, if I load through that point, there would be no twisting. If I load off that point, there will be twisting. The point is called the shear center. For the hat section, we know it's on the line of symmetry, so it's somewhere here. If I apply a load out here, it's going to twist this way. If I apply a load out here, it's going to twist this way. As the load moves towards the center, there will be a balance where no twisting occurs. And it doesn't matter what this cross section looks like. If I apply a load out here, if that load is far enough vertically high, it's going to twist to the right like this. If it's far enough vertically low, it's going to twist the opposite way like this. Somewhere in this section, it's not going to twist. That place is called the shear center. So here, that is the definition. Just as some interesting side points, the location depends on the geometry. It does not depend on the load. It is only geometry dependent. By the way, it's always located. If there is a line of symmetry in the section, it will always be on that line of symmetry. If it's not symmetric, of course, it won't be symmetric. Now, when we come back on Tuesday of next week, we'll actually go through and I will teach you how to compute the location of that shear center. And this is, believe it or not, this is one of, if there were only 3 things that you learned in this whole class that you retain going forward, one of those 3 things would be that this thing called the shear center exists, and then how to calculate it. People have lost their lives because in the days before we really understood structural mechanics as well as we do now, they weren't aware of the thing called the shear center, and consequently people lost their lives because we didn't design for it correctly. So this is a real critical topic. I want you guys to internalize it, do it well, and I'll teach you how to do it next Tuesday. Okay, that's it for today's lecture. I'll hang out for a little while here to take any questions. Otherwise, have a great weekend, and I'll see you guys on Tuesday. Ethan, hang around for a second. Just 1 second. And Chris, you too, please. Ethan, are you really, do you really have perfect pitch? For real? Wow. Can I quiz you? I could play a note on my son's piano, or I could get my phone. We'll do that another day. I'd love to see that. I've never actually met somebody with perfect pitch before, so that's really
I want to
cool.
see this too.
No pressure.
What was your childhood like?
With perfect pitch?
Well, I've heard that like people in China, because it's a tone-dependent language, they're more likely to have it. Otherwise, people in Western countries, in order to get it as a child, they have to listen to some pretty wacky music, like a lot of jazz.
Interesting.
Well, I grew up in a musical family, so that might be part of it.
So you guys did listen to a lot of probably music beyond my understanding.
Well, I don't know. I mean, my dad's a pastor, so I grew up surrounded by organs all the time. And yeah, we just listen to a lot of music.
Very cool.
What's this one? Look at that.
It was a G.
All right, got another one for you.
That one's a C.
You got it. I got another one. Oh, this one's gonna be tough.
Oh, that's an A.
Jeepers.
Bend one and see if he gets it.
What's that?
Try to throw it out a pitch to see if you can get it.
Oh,
Like,
well, here's
same time.
We're
Can
gonna
you
go
like
some,
certain chords then?
all right, here's some cognitive dissonance, right?
Sounds like you've got the G and the A going.
Very well done.
Well, that's cool.
He's basically a wizard.
C and A.
C and A. It's incredible.
See, the downside to all of this, I can't hear a song without knowing what key it's in. I can't just let it wash over me without singing the music in my head. So there's that.
Yeah. There's a mathematical analog to that. I think it's called synesthesia.
I wish I had that.
Yeah, me too. Anyway, very cool, Ethan. Thanks for sharing your gift with us. That's awesome.
Normally I'd have a piano, but that's at home. Whatever.
It's just crazy.
I have a question for you, Dr. G.
Yeah.
When you fly, we learned this morning that there's this center of gravity section where the plane is still statically stable, but to the pilot, it feels like it's not statically stable. Have you experienced that?
So ask the question again. In what context did this discussion come up?
This is in the class for aircraft stability and control, and there's this thin region denoted HN, the aerodynamic center, and then this HN prime. And if you're between these two sections, and that's where your center of gravity was loaded, the plane is still technically statically stable, but to the pilot, the controls feel reversed, or so Dr. Rose said.
Well, so I believe Dr. Rowe. I've never actually experienced that myself. Now, you have to keep in mind a couple of things. So, number one is I fly relatively stable aircraft. I haven't flown that many aircraft. The Cessnas, let's see here, 152 and 172, Piper Archer 2 and 3, and Piper Saratoga. That I think I think that's all the airplanes I've ever flown. All of those have relatively high stability margins. And of course, as a pilot, I am very diligent about loading within the CG envelope for the aircraft. And the way that they would specify the CG envelope for any of these aircraft that I fly, you would not be permitted to load in that region, I'm guessing, because that would be sort of uncomfortable and perhaps unsafe. So that's a long answer to a short question. My answer is no, I've never actually experienced it and can't describe it to you. But what I can describe for you is, we describe stall as being a singular event, like it stalls or it doesn't. And real pilots sitting in cockpits, different airplanes stall very differently. Some have a soft stall, some have a very sharp, hard stall. And it does depend a little bit on how the aircraft is loaded and, sort of what your flight condition is at that moment. And we don't really get into that aspect of describing stall as engineers, at least in this lower level aerospace courses. I suppose if you became an aircraft designer and we're studying greater detail, you might go into those details a little bit. And I do talk about that in aircraft design class. There are ways to mitigate stall so it's not a sharp stall. In fact, your goal is to have the wing roots stall first and then have the tips not stall so that you can maintain roll control kind of well into the stall region. But that's kind of the level we describe it. We don't go into much more detail than that.
We have another question too. So
Sure.
our first
By the way,
thought.
Scott, just one second. So David, are you is that in his, is this the advanced aircraft performance class, the 5,000 class, or?
This is the 4,000 level class.
4,000. Okay, interesting. Great. Thank you. Scott, go ahead.
So our initial thoughts with the Shear Center, we're taking a guess. Can you approximate the Shear Center's location based on the centroid's position? Is it close to that area?
No, you as a general statement, no, you can't. What I will say is if for closed sections, we're sort of looking at open sections, right? So this one's open.
Mm-hmm.
So when it's open like this, then the centroid, for this particular problem, the centroid would be about in here somewhere, but the shear center is way down here. If it's more of a closed segment, then your centroid is going to be in here, and your shear center is probably going to be a lot closer to it. If there's two planes of symmetry, then you're probably going to be that they might, in fact, likely would be coincident. But as a general statement, you cannot assume that they're the same location. And honestly, I mentioned that there have been fatalities associated with design because we didn't understand this concept, 120 years ago. And part of the assumption that underlies or that caused those accidents was that they would be close to each other. I mean, the whole concept of there being a shear center was not well defined at the time. So it's not like they said, well, where is the shear center? I'm going to assume it's at the same location. They just didn't recognize that these could be different locations.
Okay. All right. Thank you.
Yeah. Okay. Any other questions? Otherwise, I'm going to wrap up for the day. Chris, you going to hang out for just a minute?
Yeah, I'll stay here for a while.
Okay. All right. Thanks, everybody. I'll see you guys next week.